We start with matrix A given as a 3 by 3 matrix with entries 4, 1, 1 in the first row, 1, 4, 1 in the second row, and 1, 1, 4 in the third row. The goal is to prove that matrix A has an orthonormal eigenbasis, meaning a set of eigenvectors that are mutually orthogonal and of unit length. A key fact is that a real symmetric matrix satisfies the property that it equals its own transpose. The spectral theorem states that any real symmetric matrix has eigenvectors that are orthonormal and correspond to real eigenvalues. These eigenvectors form an orthonormal basis for the entire space of real n-dimensional vectors. To diagonalize matrix A, we need to find its eigenvalues by solving the characteristic equation given by the determinant of a minus lambda times the identity matrix equals 0. We write the determinant of the matrix with entries 4 minus lambda, 1, 1 in the first row, 1, 4 minus lambda, 1 in the second row, and 1, 1, 4 minus lambda in the third row, and set it equal to 0. Calculating this determinant results in the expression 4 minus lambda to the power of 3 plus 2 minus 3 times 4 minus lambda equals 0. We rewrite the equation as 4 minus lambda to the power of 3 minus 3 times 4 minus lambda plus 2 equals 0. Letting x equal 4 minus lambda simplifies the equation to x to the power of 3 minus 3x plus 2 equals 0. Factoring this cubic polynomial gives the factors x minus 1 squared times x plus 2 equals 0, which means x equals 1 with multiplicity 2, and x equals negative 2. Substituting back for lambda, we find lambda equals 4 minus x, so the eigenvalues are 3, 3, and 6. Next, we find the eigenvectors corresponding to lambda equals 6 by solving the equation A minus 6 times the identity matrix times vector v equals 0. This leads to the matrix with entries negative 2, 1, 1 in the first row, 1, negative 2, 1 in the second row, and 1, 1, negative 2 in the third row, multiplied by vector v equals 0. Solving this system shows that the eigenvectors are scalar multiples of the vector with all entries 1. For lambda equals 3, we solve the system A minus 3 times the identity matrix times vector v equals 0. This gives the matrix with all entries 1 in every position multiplied by vector v equals 0. The eigenvectors satisfy the condition that the sum of the components v1 plus v2 plus v3 equals 0. We choose two basis vectors for this eigenspace as vectors with entries 1, negative 1, 0, and 1, 0, negative 1 respectively. To make these vectors orthonormal, we divide each by the square root of 2 to normalize their length to 1. We define u1 as 1 over the square root of 3 times the vector with all 1s, u2 as 1 over the square root of 2 times the vector 1, negative 1, 0, and u3 as 1 over the square root of 2 times the vector 1, 0, negative 1. We form the orthogonal matrix P by placing vectors u1, u2, and u3 as its columns. Matrix A can then be diagonalized as P times diagonal matrix D times the transpose of P, where D has diagonal entries 6, 3, and 3. To compute A to the power of 10, we use the diagonalization and write it as P times D to the power of 10 times the transpose of P. The matrix D to the power of 10 is diagonal with entries 6 to the power of 10, 3 to the power of 10, and 3 to the power of 10. We begin with a real symmetric matrix, so the spectral theorem applies. Its symmetry guarantees an orthonormal basis of eigenvectors. The eigenvalues are 6, 3, and 3, with a repeated eigenvalue spanning a two-dimensional eigenspace. In this orthonormal eigenbasis, the matrix becomes diagonal. Raising the diagonal matrix to the 10th power makes the final computation immediate.